Low Earth orbit, LEO, satellites like the Starlink constellation are revolutionizing modern warfare by integrating commercial networks for defense purposes. Operating below 2,000 kilometers, LEO satellites offer lower age of information and higher bandwidth compared to traditional geostationary satellites at 35,786 kilometers, enabling global coverage. This is invaluable in military operations where conventional communication infrastructures are compromised. For instance, over 150,000 Ukrainians use Starlink daily as of May 2022 for communications, enhancing their situational awareness and strategic decision-making on the battlefield. Numerous military applications, like Delta and Kropiva, leverage Starlink to provide enhanced battlefield awareness and real-time command controls when terrestrial networks are unavailable. However, integrating commercial LEO satellites directly into military operations poses significant security, bandwidth efficiency, and latency challenges. Ensuring information confidentiality requires robust encryption because a compromise in any single device could lead to information leakage. Traditional end-to-end encryption, E2EE, secures data and facilitates access to the information with unique cryptographic keys for each receiver. However, the scalability of E2EE becomes a bottleneck as the number of participants and dynamic changes in group membership increase the complexity of key distribution, management, and revocation. Moreover, the need for unique sessions between each receiver and the satellite complicates communication efficiency due to limited satellite access capabilities and orbit capacity. Therefore, we propose StarCast, a secure and efficient multicast system for LEO satellite networks. Our system considers a modern battlefield, or the situational awareness system utilizes advanced detection platforms such as the Aegis Combat System and the Airborne Warning and Control System, AWACS, which can effectively surveil enemy targets on the battlefield and generate intelligence for military operations. An intelligence controller within the situational awareness system determines the access policy for combat units based on their corresponding privileges. During military operations, all information is encrypted and only the legitimate recipients who satisfy the access policy can decrypt the ciphertext intelligence.
In StarCast, ciphertext policy attribute-based encryption, CP-ABE, is the cryptographic foundation to achieve the goal. We demonstrate the system workflow as follows. In the military operation preparation phase, the intelligence controller sets up the scheme's security parameters and generates a public key and a master key. The intelligence controller then issues secret keys to each combat unit based on its corresponding attributes. During the military operation phase, the intelligence controller formulates the access policy for intelligence provided by the situational awareness system and integrates this policy into the ciphertext. Subsequently, the encrypted intelligence is multicast to combat units through LEO satellites. A combat unit will decrypt the ciphertext intelligence only if its attribute secret keys match the attached access policy. For instance, we can define the access policy for a combat unit eligible to access the intelligence as follows. The soldier should be part of Task Alpha and either be the team leader or a member of Team Blue, expressed as the access policy. The ciphertext can be successfully decrypted by a combat unit whose attribute set includes Alpha, Blue, Leader, but not by a unit with attributes Beta, Blue, Member. We prototyped the StarCast system using the Starlink Gen 3 Standard Kit. We deployed a MacBook Pro as an end device, connecting it to the Starlink antenna and its Wi-Fi router either via a Wi-Fi signal or a plug-in cable. Additionally, we utilized 8 Amazon Web Services servers located in Virginia, Ohio, California, Canada, London, Frankfurt, Tokyo, and Singapore to evaluate the end-to-end age of information. We observed that Starlink's age of information is slightly higher than that of the 5G network and indoor Wi-Fi on average. However, the variation in Starlink's age of information is much greater than that of the 5G network and indoor Wi-Fi. In rural areas, where 5G networks are unavailable and the only terrestrial wireless network service is a weak T-Mobile LTE signal, it exhibits significantly higher age of information on average and greater variation compared to other methods. In contrast, Starlink consistently provides reliable network service, even in rural areas. Our cryptographic design ensures that key generation and encryption times scale linearly with the number of attributes, while setup and decryption remain efficient with times under 80 milliseconds, demonstrating the system's feasibility and effectiveness.
Thank you for watching.